So, welcome to my little talk about full disk encryption. We are going to learn today how to encrypt a drive and also how to sort passwords. Yeah, first of all, what is the full disk encryption? It's a general term for encryption of all data on hard disk drives and soft state drives, and yeah, it kind of differs from a usual encryption that you know, where you have two parties and you kind of send message over unsecured channel over between two different locations. I don't want it to be read, and full disk encryption is different. You have mostly only one party. For example, you are communicating with a future self, and your goal is to encrypt between two different points in time, and you save data on the hard disk and kind of try to keep it being unread by another party and between two different points in time. And to achieve this, we have to solve some problems. First of all, usually RS keys if you encode them, they are for example in hexadecimal. You encode them with hexadecimal numbers. They are just an arbitrary string of they will just be a arbitrary string of characters, and unfortunately the capability of humans to remember arbitrary characters doesn't scale at all, and humans need some mnemonics and structure to remember things. And then there we come to the next problem. User passwords usually don't have enough entropy. Entropy is basically a measure for the unpredictability of a password domain, and the unpredictability of the password domain. The problem is that user passwords usually are only 8 to 11 characters long, which is actually only half of the size necessary to have as security like an RS key. If you look at this diagram here, I can also later explain you this formula if you are interested in the discussion. And you have to have a problem that later we're going to see a method, and this method has to solve some problems that we are going to discuss later. And the final question is also if it then also prevents brute force attacks. And also a word about the entropy. And also, besides not having enough length, probably these passwords also come from sources with low entropy. They might be words from a dictionary, have some predictable structure, birthdays, and so on. And then another desirable property is to be able to change passwords. That's the so-called re-encryption problem. You don't want to re-encrypt the whole drive if you change a password or a configuration. Then the next thing we need is a proper cipher mode. And cipher mode becomes relevant as soon as you have data that is longer than a cipher block, and the cipher block is, for example, an IS block of 16 bytes. And then you need a cipher mode, and the cipher mode is basically the way you utilize a block cipher. And then mostly have another parameter, the initialization vector, to add variability. And one property probably most cipher modes satisfy is that they hide plaintext symmetries between different cipher blocks. And I guess I guess the most straightforward cipher mode is probably the electronic codebook mode, and that's basically just the idea that you divide the data into blocks of cipher block size and encrypt them with the cipher. But this property most ciphers probably satisfy is that they hide plaintext similarities between different locations, because the problem of electronic codebook mode is that the same plaintext gets encrypted to the same ciphertext, and then you can still recognize this penguin, but you actually want something like this here. And yeah, and thus is a desirable property to hide plaintext similarities between different cipher block locations. Then the next desirable property is that then the next desirable property is that no plaintext information also plaintext similarities are hidden over time. Many cipher modes don't satisfy this property. A really bad example is, for example, the counter mode. And the counter mode has this encryption formula. And the problem is, if you have the same cipher mode, a cipher block, it has here the same counter, and then this encryption result here just cancels out, and then you have plaintext XOR plaintext, and if at the beginning the plaintext was just 0, number of bit vector of zeros. For example, if you just bought the drive and later wrote something to it, then you would be able to just read the plaintext directly. Yeah, then another desirable property is to have random access and parallel encryption and decryption possible. There are many. There are, for example, in order to prevent this, that plaintext similarities are visible, there are ciphertexts like cipher blockchaining mode where one encryption of a cipher block is dependent on the previous encryption of a cipher block. Is dependent on the ciphertext from a previous decryption. The problem about that is that you can't. Drives usually allow random access, and that's actually a pity to lose this property. But here, if you want to write to a certain encrypt a certain location, you would have to encrypt all prior cipher blocks. And and basically for the same reason, the same problem also applies for parallel encryption. Then another problem we have to solve is this. Then there's another problem we have to solve, and therefore I have to first explain something. And that is that on drives, data gets basically accessed via logical block addressing, and a logical block is the smallest unit that you can access, and this logical block has a size of, for example, 512 bytes, and that means that 32 16 bytes IS blocks fit into it, and proper cipher mode would have to somehow deal with this size gap. Then here we have a little overview, a little checklist of all the properties, and we are going to update it with check marks as soon as we find the proper method that solves our problems. Then our first method is the password-based key derivation function 2, and this password-based key derivation function 2, if you remember, one of the problems was that the password domain has too low entropy. The problem about that is that brute force operations are then possible to execute on it. And a pretty obvious idea is to just increase the computation time of a brute force operation. A brute force operation looks like this. You have a first step, you have a function that maps passwords to keys. This is a so-called and keys. Then you decrypt the cipher block, and then you check result against possible outcomes. But we can't do much about this last two bullet points, but we can do something about to increase about the first bullet point, and then there we can just replace this function f by a CPU and intensive transformation password-based key derivation function 2. From now on, I just say password key derivation function instead of 2 to save time. And and this password key derivation function 2 has a parameter I, and this parameter I is the intensity, and it defines how it fine-tunes how high the computational complexity and thus also the computation time of this transformation is. It also has a second parameter, the salt, and the salt additional parameter, the salt, and the salt is necessary because you can unfortunately circumvent this password-based key generation function, this CPU-intensive computation that needs time, by using a rainbow table that maps password to keys. And here, for example, to map all password to keys up to length, all passwords up to length 11 to keys, you would actually need 113 bytes. I guess no one of you has this much storage. I don't think so. But actually, I think not even Google has this much storage. From what I know, it has like 40 estimated storage of 46 exabytes only. That's one below bytes. And the problem, actually, if you keep in mind that you actually only have to search through a subset of the password domain, because passwords often have predictable patterns, are from a dictionary. Then it's actually you can have a good chance of success with just a subset of this big set of password domains, so it would need less time. And the trick is about the salt value is that you make this key generation function dependent on the salt parameter s, and the salt parameter, and then this rainbow table would have to map password salt to and salt to keys, to a key. And the thing is that with every bit of this salt parameter, the storage requirements double. And typically a salt is 16 bytes long. That's for information. And here you see a rainbow table, for example, as example. And then another thing, and if you're interested why we call it salt, it's really like you think, one would think. It originates from a culinary practice of salting food to enhance flavor, and analogously you can also salt a password to enhance security. And here we see how the password-based key generation function is defined. It looks quite complex, but it's actually quite simple. This hj function actually just defines that you iterate a pseudo-random function. And a pseudo-random function is basically a function that, a keyed function that can't be distinguished from random, from a random function. And it's keyed because to enable that you can share it with different parties and don't have a problem that a person who doesn't have a key will you basically have uncertainty. By the key you kind of add uncertainty if a party doesn't have a key, and so you can share it with different parties. And basically and you iterate it. And one thing, and mostly you use the designers of a password based key generation function didn't want to put too many assumptions on the underlying function, and restrict it too much, and thus they just said it has to be a pseudo-random function. But basically mostly you use a hash function used in HMAX setup, and the HMAX setup of a hash function is basically just to turn a hash function into a pseudo-random function. And the hash function is really suitable for that because it can map arbitrary input like a password to a fixed size input. And yes, and you kind of iterate it. The output of one pseudo-random function is the input of the next one. But there's actually a problem. If you kind of iterate it, the range of reachable values becomes smaller and smaller, and thus the designers thought about XOR, applying XOR to all intermediate results, such that values outside this darker blue area here are reachable. And lastly, there's this concatenation. That's actually only necessary if you this concatenation is only necessary if the hash function output is less than the key that you desire. And yeah, it adds here different counters. It counts up, and that are basically different applications of this iterated functions, and you count this counter up so that you don't have a repetition. And because of the avalanche effect, yeah, small input change results in a big output change. Yeah, and this password key derivation function basically satisfies. We can then set here all check marks. Besides the brute force attack, there we just still have to evaluate whether it actually saves, secures us from brute force attacks. Then we come to key hierarchies, and key hierarchies solves this encryption problem we have previously talked about. And this key hierarchy basically has two layers. It has a key encryption. It has a layer of key encryption keys and a layer of one data encryption key. And basically the idea is that this data encryption key is basically treated like data and saved in the key partition, and it is itself used to decrypt the data in another partition. And you basically use this key encryption keys to decrypt or encrypt the data encryption keys that are saved here. And yeah, and you have if you have multiple such partitions, you also have if you have multiple key encryption keys, multiple partitions, you basically have multiple passwords to access this data encryption key. And basically, I don't want to go into too much details. I can later in the discussion explain this to you. But basically, the idea this what you see here is pretty intuitive. Yeah. You basically always have this data encryption key, and you try to access it with a password key derivation function by inputting the right password, and then you get the right key encryption key and get the data encryption key, and then you can basically access your data. And key change is also quite self-explanatory as soon as you look at it. You can basically imagine it yourself. Yeah, then we come to the XTS Cipher mode, which might be our desired Cipher mode that satisfies all of our properties. Yeah, the XTS Cipher mode is built about the XOR encrypt XOR construction. I call it from now on XEX construction to save time. And this the name basically says everything you need to know. You input a plain text, then you XOR it with a tweak, then you encrypt it, and then you XOR it with a tweak again. And the security is basically based on the single key even Mansour scheme, which has the public recommendation and the secret key. And because of the secret key and this even Mansour scheme has the security proof, and if our XEX construction also has its tweak to be secret like this key, then the XEX construction is also secure because of the security proof. And yeah, and this XEX construction is basically used to turn a block cipher into a tweakable block cipher, and that has a tweak parameter delta, and the tweak is basically there to add variability to this cipher mode, and is basically here to add variability to this applications of the cipher, and the key is there to add uncertainty to applications of the cipher. To the package of a cipher. And the tweak doesn't necessarily have to be secret like the key, but because of the secret Mansour scheme, it actually has to be secret. And then maybe a little quiz for the audience. Do you see the XEX constructions here? Is it maybe here, or is it maybe here? A or B? Yeah, it's B. It's you can see the XEX construction over here. And yeah, on this slide we see how the encryption and decryption looks like. And and you see these parameters I and J. They derive from this logical block addressing. I is a logical block address, and J is the relative index of a cipher block within a logical block. And J is used to hide plaintext similarities within one logical block between cipher blocks, and I is used to hide plaintext similarities of the same relative index cipher block between different logical blocks. And yeah, and to achieve this hiding of plaintext similarities, one needs a so-called we need some math magic, we need finite field theory, and we need special elements that are called primitive fields, and they have a special property, and this property is that they are able to they are basically generators, and they are able to generate a sequence of all elements of a field without repetition. And that's possible by applying the by exponentiation with this j parameter, and for this it needs a proper multiplication for a finite field, and we get a reliable multiplication for a finite field with the help of polynomial field multiplication. But I don't have the time to explain this now, but if you're interested, I can later explain this to you. And usually for XTS cipher mode, alpha usually is 2. And now we have a sequence of field elements without repetition, but we also need something else because this sequence is always the same. So we kind of need to always have a different sequence. And if you remember, this tweak from before, this tweak also has to be secret. So we need a second key K2. With this key K2, we encrypt the logical block address I and get a secret element B. And with this secret element B, we can actually achieve to get a secret sequence of field elements. And we do this by using a field property, and that is a derived field property, and that is if you multiply a field element with the same field element with every other field element, you get a permutation. And thus we get a random a secret permutation, a secret sequence of this field elements. And actually we only need 32 of them because the logic block only has 32 IS blocks. We only need 32 field elements or tweaks. And here you see how this XTS cipher mode basically looks like. For several cipher blocks, and here I actually have to make a confession to you. I'm actually not going to explain the full XTS cipher mode to you because it also has ciphertext stealing, and I'm also only going to explain to you basically the text construction executed in tweaked codebook mode, and this tweaked codebook mode is basically just what we've just saw to hide plaintext similarities by calling every tweaked block cipher with a different tweak calculated from this INJ. And here we have our overview again, and we see that the exact cipher mode satisfies most of our properties, but we can't surely say if it also hides plaintext similarities over time. And now I come to a conclusion if our methods are actually worth anything. And first we come to the password-based key diversion function, and the problem about it is that it can be implemented as a small circuit with very little RAM, and thus brute force attacks with help of ASICs and GPUs are really cheap. But there's actually a better alternative to it, and that's Argon 2, and Argon 2 has several parameters. One of them is the memory required, and it has proven memory hardness, and thus if you try to execute it efficiently, you will at least need a certain amount of memory. And then we also have to talk about whether this brute force attacks are really prevented by the password-based key diversion function. Here I made a graph, and this graph I assumed that here I have a graph, and in this graph I assumed that a user delayed boot of the attack to 1 second and has the computational resources that are currently used for Bitcoin at his sleeves. And I found out that you can, with this computational resources, an attacker can within 5.5 years find out passwords up, in worst case, all passwords up to length 11. Yeah, but that's really good scenario for an attacker. But yeah, basically this computational resources, it's maybe unrealistic, but these computational resources are basically available on this planet. And then I made the same, but if the attacker has the same procedural resources. And yeah, there I found out that if you have no growth, technological growth, then you need 160 trillion years. And if you have technological growth, you have in between 90 and 400 years. So basically for your lifetime, if you, for example, growth assumption of that this Moore's law continues, if you have this growth assumption, technological growth assumption, then you can estimate that for your lifetime your passwords up to length 11 will be secure. Then I come to the XTS Cipher mode. Here I would recommend to only use it for full disk encryption, because for files, if you encrypt on the file level, then Cipher mode then it's recommended to use. It's more recommended to use the Cipher mode of authentication, and that allows fully randomized encryption. And if you encrypt on the file system level, it's more recommended to use the encryption options of the file system, because they have format awareness, and it's basically recommended to always encrypt on the highest possible level, else you will lose flexibility to choose the right encryption for a file format or authenticate your data. And yeah, and XTS Cipher mode also has fewer security guarantees than other modes, because yeah, also due to the missing authentication, you can use chosen ciphertext attack. You can execute chosen ciphertext attacks. Plaintext similarities are still visible over time, and you can also see much more fine-grained cipher block size changes within in this cipher blocks of a logical block. For example, here we have over time. Here over time we have the same cipher blocks, and here you see that here this small change can here, for example, this TE and XT cipher blocks didn't change, and then you can still see that the cipher blocks keep the same. And for a fully randomized encryption of a logical block, this wouldn't be the case. And the same, and you can't see that here there was some cipher block kept the same. Yeah, and all in all, I would say, yeah, it depends on the security requirements of a user. I guess for most users, XTS Cipher mode and password-based key derivation function satisfy all requirements. but if you have higher requirements to have something secure for million years and don't have it visible and don't have fine-grained changes visible, then you probably need and want to authenticate your data, then you probably should use another Cipher mode. But for me, I would actually use this setup. Yeah, then thanks for your attention, and are there any questions?